Hello. My name is Eugenie Rinie Anum with matrix number 102,551. I am too shy to show my face explain the convolution of signal. So I will explain through this genius professor.
Alright, let's cut to the chase and talk about convolution, one of the most fundamental ideas in signal processing and deep learning. What is it, really? Look at the definition here. Convolution is a fundamental mathematical operation that combines two signals. We call them the input signal and the system's impulse response.
The whole point is to mathematically figure out how the system changes or processes that input. If you look at the graphs below, we take a simple square wave input, apply the system's response, and the final convolution output shows us the result. It's how systems respond to input. Simple, right? Now let's see how do convolutional of signal works. It actually have for states which are flipping, shifting, multiplying and integrating or sum. Now, we're diving into the core operation behind image processing and convolutional neural networks, to deconvolution. It's the engine that allows systems to detect patterns, like edges, curves, and textures within data. Our goal is to transform a large input matrix, like an image, using a small kernel, our feature detector, to produce a smaller output feature map. We start with the kernel itself, and the first step is essential to what defines convolution mathematically. 1. Flipping. We conceptually rotate the kernel 180 degrees, that is, we flip it horizontally, and then we flip it vertically. This transforms the original kernel into our flipped kernel. Now, you might ask, why do we flip it? This is a common point of confusion. If we didn't flip it, the operation would be called cross-correlation. The flip ensures that the resulting output correctly accounts for the system's temporal or spatial response to the input. For instance, in signal processing, it makes the output accurately reflect how the system's past input influences the current output. In neural networks, while it's often skipped in practice because the kernel values are learned and symmetric, conceptually, the definition of convolution requires this flip. With our flipped kernel ready, we move on to shifting. The kernel acts as a sliding window across the input matrix. We place the kernel at the top left corner, covering the initial segment of the input matrix. This is our first calculation position. We then systematically slide this window across the input. The amount we move the kernel each time is called the stride. For simplicity, we often use a stride of 1, meaning we move 1 pixel or 1 position to the right, then perform the calculation and repeat. Once we hit the end of the row, we drop down 1 step and start over from the left. The key here is that the kernel is our observer, meticulously scanning every single region of the input matrix to check for the feature it's designed to detect. When the kernel is stopped at any given location during the shifting phase, the core computation happens. 3. Multiplying. This is an element-wise product. We take the numerical value in the top left cell of the kernel and multiply it by the numerical value in the top left cell of the input matrix directly beneath it. We repeat this for every single corresponding cell within the kernel's window. Think of the kernel's values as weights. By multiplying, we are weighting the importance of the input data underneath it. High weights in the kernel will amplify certain input values, while 0 weights will ignore others. This element-wise multiplication is crucial for feature detection. Finally, we arrive at 4, summing. After all the corresponding elements have been multiplied, we take all those resulting products and add them together. This single resulting sum becomes 1 single entry, 1 pixel in our smaller output feature map. This number represents the activation or detection score for the feature, defined by the kernel in that specific region of the input. We then go back to step 2, shift the kernel to the next position, and repeat the multiplying and summing until the entire input matrix has been processed, resulting in our final compacted feature map. And that, in a nutshell, is the 2D convolution principle. Now, let me explain about the application. The first critical area is signal filtering. which deals with one-dimensional data like audio or sensor readings. This process involves creating specific filters such as low-pass or high-pass. Filters by designing a filter kernel or impulse response. Convolution is then performed using this kernel to process the raw signal, primarily with the goal of removing noise for data cleanup, or to effectively isolate frequencies to extract specific information. This technique ensures that engineers and scientists are working with clean, reliable, and targeted data. The second area is image processing, which extends convolution into 2 dimensions. The image acts as the signal, and we use a 2D kernel filter matrix that is convolved across the image data. By selecting different values within the kernel, specific visual effects are achieved. This includes blurring for smoothing, sharpening to enhance fine details, and perhaps most importantly for computer vision, edge detection, which isolates the sharp boundaries of objects. This capability is essential for any automated system that needs to visually segment or interpret the content of an image. Finally, convolution is indispensable in both physics and engineering and deep learning. In physics and engineering, it is the primary mathematical tool for modeling systems. The operation allows us to predict the output of a system by convolving the input with the system's characteristic response, as demonstrated by modeling the behavior of sound in a room acoustics or analyzing vibrations in a mechanical system. Meanwhile, in deep learning, convolution forms the core of convolutional neural networks (CNNs). CNNs use convolution to perform automated feature extraction in image recognition, where the kernels are learned automatically to detect hierarchical patterns, from basic edges to complex objects, propelling the field of artificial intelligence. Let's quickly wrap up. The 2D convolution principle is defined by 4 sequential steps: flipping, shifting, multiplying, and summing. Remember, we flip the kernel conceptually, then shift it across the input. At every single stop, we multiply the overlapping elements and sum the results to produce one output value. This process transforms the input matrix into the output feature map. Why does this matter? Because convolution allows us to extract features locally and systematically. Each kernel acts as a specialized filter, finding exactly what we train it to find, like edges or corners. This incredible ability to condense raw data into meaningful feature maps is the single most important reason why convolution is the foundation for all modern image recognition and computer vision systems. Oh, you don't forget that we can perform convolution by using MATLAB and also manual calculation.
Thank you for watching. Say bye-bye to Professor.
Goodbye.